right. Hello, everybody. So we're now in our approximation algorithms unit. But I'm going to start with a little out of order activity. I finished up simplex and the ellipsoid algorithm last Wednesday. But I didn't have time to give you a quick overview of the third approach to linear program solving called interior point. So I'm going to take 10 or 15 minutes for that. And this is really just going to be conceptual. There won't be any, I won't be proving anything at all about this technique, but I think it's useful to understand what is involved in this, what is involved conceptually in this third approach to linear programming. And then we will return to your regularly scheduled approximation algorithms programming. So short lecture on interior point. We saw in simplex this approach that moves along the edges of a polytope from vertex to vertex. And that seems to be sort of tied up with the inherent complexity of the polytope, right? We talked about how the diameter of the polytope sort of determines the best you could possibly hope to do with the simplex algorithm, and about how the running time is basically determined by the length of these paths from along the vertices of the polytope. The ellipsoid algorithm managed to avoid all of that. It sort of stayed, in a sense, it was doing this binary search approach where it was not even in the polytope, but it was just sort of, it used this nice shape of an ellipsoid, which didn't have all of these weird vertices, these corners, and instead just looked at the centers of ellipsoids and slowly shrank the ellipsoid until it landed inside of the feasible region of the polytope. Interior point takes an entirely different approach to avoiding the complexity of all of these pointy corners that the simplex algorithm has. It solves a linear programming problem by staying in the interior of the polytope. In this sort of nice, smooth area that's far away from all of the corners of the polytope. And like, again, if you think about our physics analogy, right, when you drop the ball, it kind of rolls, and every time it hits a corner, it has to change direction. And that sort of represents some computation that you're performing at each corner of the polytope. If instead you could have it fall through the free space in the center of the well, it could just sort of fall straight down and wouldn't need to run into these corners. And in fact, you can continue the physical analogy. Right? With simplex, we were dropping a ball in the polytope and letting it fall down, and it sort of would bounce along all of these corners on the way to the bottom. What interior point does is it puts a magnet underneath each of these constraints that creates a long distance force that pushes the ball away before it actually runs into the walls. And so instead of falling down and bouncing off each of these corners, in interior point, your ball is going to trace a smooth path through the air that just sort of slowly shifts towards the optimum. Okay. The first of these was by Karmakar in 1981. As I mentioned last time, it generated a tremendous amount of news coverage, all sorts of over-the-top, now we can solve traveling Selson problem in polynomial time, all sorts of things that were wrong. But it was a really tremendous breakthrough. The key idea is to replace this large collection of annoying and complicated linear constraints and replace them with a single objective function that encapsulates all of the constraints and gives you an unconstrained optimization problem. But the way they do that is by making the objective function nonlinear. So the key idea was to define this thing called the logarithmic barrier function. And this, again, is for a standard form linear program. We know how to transform into standard form linear programs. At a particular point x, you define the potential to be your actual objective. That's the thing that you want to minimize. But you add what's called a barrier term, where you take the sum of the logs of the xj's. Okay? Now remember, we're in standard form. So at any feasible point, all of the xj's are non-negative, right? So what is the effect of this barrier term? Okay. Once we've defined this potential, the approach of interior point is simply to minimize this potential and not worry anymore about constraints. Just say, find the x that minimizes this potential. Okay. So what is the effect of this second term on this minimization problem? Right, if we didn't have the second term at all, then we would just be minimizing Cx, which is what we're supposed to do in linear program. How do things change if we add this term? Yes?
Pushes it into the interior.
Right. So this term says that if xj gets very close to 0, then log of xj, or sorry, let me start from the other side. If xj is very large, then it doesn't really matter how xj changes, right? You're still going to be subtracting off something. You can still be minimizing this. But if xj gets very close to 0, then log of xj turns very strongly negative, right? Heads towards negative infinity. And so essentially, if you get too close to one of the constraints, too close to one of the barriers, right, then the second term cancels out or overcomes your efforts to minimize the linear objective by just sort of adding a large value to it. So this says that whatever you achieve in minimizing this logarithmic barrier function, you're going to do it without getting too close to the walls of the polytope. Okay. However, subject to not getting too close to the walls of the polytope, you are going to try to minimize this objective function. So this really implements the magnets that I drew in the picture, right? Now let's think about the role of mu. Okay, so mu basically tells you how important these two terms are, right? If mu is very small, then your magnets are very weak, and the main driver is going to be to minimize the linear term. Okay. If, on the other hand, mu is very large, the magnets are going to be so strong that you won't even care about the linear term. You're just going to try really hard to stay away from the walls of the polytope. And in fact, as mu gets very large, the linear objective becomes irrelevant, and the optimum of this turns to be what's called the analytic center of the polytope, right? The point that is as far as possible from all of the constraints. Okay? But again, the nice thing about this is that it moves all of the inequalities, right? We still have the requirement that AX equals B, right, which exists in standard form. But we no longer have any inequality constraints, right? We're just saying over this linear subspace, AX equals B, minimize a single function, which, again, it's only one function, which is great. It's a nonlinear function, which makes it more complicated. Okay. So does that make sense, the general idea? Okay. And what our sort of long-range goal is, we're actually going to be playing with this term mu. Or sorry, what we're going to do is we're going to make mu small, so the Cx term dominates, and you really do end up minimizing the objective function. Okay? But since mu is not 0, you do have this second term, and you avoid ever crossing the constraints. The effect is that the optimum is near the actual minimum of Cx, but is also feasible. Thanks to the barrier. Okay. So how do you minimize a function like this? That's right. How do you do it?
You could maybe do gradient descent.
Exactly. So minimize via what's known as gradient descent. Okay. You have a current x. You compute the gradient. At your current x, right? And then you move in the direction of that, in the decreasing direction of that gradient. Okay. Now, of course, you have to project that gradient into the ax equals b subspace, because that ensures that your point will stay feasible. Okay? So it's really a very simple algorithm, right? Because the gradient itself, right, what is the gradient? Right? Well, the gradient of a linear function is just that linear function, right? You move in the direction of c, but you also get these mu divided by xj terms from the second term. And so those are basically saying, well, you don't move exactly in the direction of minimizing the linear objective. You also are moving to stay away from, you're moving in a straight line, but a straight line which is chosen to keep you from getting too close to the barriers. Okay? And then it turns into math, because what you have to figure out is how far can I move in the direction of the gradient and still have the gradient be accurate, right? We have a nonlinear function here. So long as the gradient is a good approximation to that nonlinear function, any progress that we see by moving along the gradient is going to correspond to progress on the nonlinear function. But at a certain point, the gradient becomes too different from the nonlinear function, and then it might appear that we're progressing on the gradient, but we're not actually progressing anymore on the nonlinear function. So that defines the step size that you can take in your gradient descent. Okay. Now, another problem, so let me put challenges here. One is to figure out this step size in the gradient descent. How far can you go and still have it be accurate? That's just math. The other challenge is that we are required to maintain ax equals b. So we project our gradient into the ax equals b subspace. So what could go wrong if we're projecting our gradient into the ax equals b subspace and then trying to move in that direction? Well, yeah?
It may be perpendicular.
Yeah, what if the gradient is perpendicular to ax equals b? Right? What if it looks like the way to minimize the objective function is to abandon the feasible region entirely? Okay. All of a sudden, it looks like you can't make progress at all. Okay. So in Karmakar's early work, what he essentially showed is that the portion of the gradient that is perpendicular to ax equals b is a kind of gradient for the dual solution to the linear program. Okay? You remember how in simplex we sort of a dual solution emerged from the being in the optimum place in the primal, right? Well, similarly, it turns out that the gradient that you're looking at can be decomposed into sort of a primal part of the improvement, an improvement in the primal feasible solution, and the improvement in a dual feasible solution that you're hanging on to at the same time. So Karmakar used what's called a primal dual. Where he said, well, yeah, you take this gradient, and if a lot of the gradient is inside the ax equals b subspace, then you can get a significant improvement in the primal solution. If, however, the gradient seems to be perpendicular to the AX equals B subspace, then you can use the perpendicular part to give yourself a significant improvement to the dual solution. And so you're actually explicitly optimizing the primal and you're simultaneously finding optima to the primal and the dual solutions as you go. Okay. Now, more recent methods for interior point use a new idea called the central path. And this turns out to be more elegant and sort of more mathematically elegant and to convey some other nice intuitions. Notice that for each mu, there exists an optimum point minimizing what I will call G sub mu of x, right? And so you can imagine varying mu, okay? And as we discussed before, if you start with mu equal to infinity, you're starting at the analytic center of the polytope. And you then take mu down to 0 continuously. When you're at infinity, you're at the central point, you're at the analytic center. When mu, in the limit, as mu goes to 0, you're just optimizing Cx, but you're also staying in the feasible region, right? So this is going to trace a path from the analytic center to the LP optimum. Okay? And so central path algorithms actually trace out this path algorithmically. A particularly common approach is what's known as the predictor-corrector approach, which is, again, a kind of gradient descent. What you do is you envision that there's some weird central path in your polytope, okay, going from the infinite point to the 0 point for mu. You're currently on a certain point on this central path. You have found the optimum for g mu of x for some value of mu. So now your goal is to figure out how to make mu a little bit smaller and find the optimum for g mu of x at that smaller mu. And how do you do that? Well, you compute the gradient of this line that's being traced out. Okay? And that's known as the prediction step. Okay? You take a linear approximate, you use the gradient to give yourself a linear approximation to the central path at your current point. You walk along that linear approximation some distance, and then you correct yourself back to the central path. Okay? If you think about it, being on the central path, again, it involves minimizing this thing, so you know that it's a minimum at a certain value of mu, so it has its gradient. You get back on the central path by saying that the gradient of something is 0 because you're at the minimum of something, right? So you get this linear system to force yourself back to having a 0 gradient, and that puts you back onto the central path. Okay, and again, what determines the runtime of this algorithm is the length of the prediction step. That's what determines the runtime of the algorithm, right? If you could take really large predict steps, you would be improving mu by a significant amount on every step, and therefore you would get to mu equals 0 quite quickly. If you have to take small steps, then it's going to take you a very long time. Okay? After a lot of math, you can show that about square root of n steps suffice to let you get very close to 0. And what does very close mean? Well, it means very close in the same sense as we talked about with the ellipsoid, right? This is, again, a weakly polynomial algorithm, right? So the difference that you get is less than the least significant bit of precision that is needed for the vertices of the polytope. Sorry, and I forgot to put in a bits here. So like ellipsoid, this is a weakly polynomial algorithm. And essentially, root n steps of interior point correct one more bit of the numbers in the answer. And so the number of steps that you take is proportional to the number of bits needed to represent vertices times the square root of n, right? Once you are close enough to a vertex so that your errors are smaller than the smallest significant bit, now you can round your solution to an actual vertex using the same techniques as we talked about. You remember we showed if you're not at a vertex, you can move to a vertex by rounding your solution, in a sense, without making the objective worse. Okay, that's something that we proved about. We said that if you have any point in the feasible polytope, you can round it to a vertex of no worse value, right? And so you use that technique to get yourself an actual vertex that's not going to be on the central path once you're close enough to it. Okay. And so, unlike ellipsoid, which was theoretically awesome but practically not, these interior point methods have become really effective in practice. And it's hard to know, and you kind of need to try both to see which one is going to give you better performance on any particular linear programming problem. So the canonical linear programming platforms or tools give you both, so that you can use whichever one is more suited for your particular problem. Okay. So that's the conceptual story of interior point. If you want to actually learn it, of course, you can go and take a real optimization class where they will go into it in much greater detail. So any questions about it before we put that away and move on to approximation algorithms? No? Okay. So on Friday, you got your introduction to approximation algorithms. We're no longer focusing on best possible runtime. Instead, we're looking at problems which can't really be solved exactly in polynomial time at all, unless p equals np. And I am assuming for the purposes of this class that p is not equal to np, so that I don't have to keep on saying that over and over again. So I'll just say it's not possible to get approximations, to get exact solutions to these problems in polynomial time, and you'll know what I mean. And we defined approximation algorithms, right? An approximation algorithm is just an algorithm that gives some kind of feasible answer. But the question that we're going to be focused on is the quality of the approximation. And last time we started by looking at additive approximations. You saw a few examples of problems where you could actually find a solution which was within some additive factor of the optimum solution in polynomial time. But you also saw reasons that most of the problems that we work on do not have additive approximations. Some problems have additive approximations, additive approximation algorithms, but usually, and this is just usually in practice. I mean, you can come up with as many imaginary problems as you like that do have additive approximations, but usually in practice, you can amplify any additive approximation into an exact algorithm. since we have said that these problems don't have exact algorithms, that means that they also are not going to have additive approximations, right? And so instead, we focus on relative approximations, right? The idea of a, the idea of a relative approximation is that on any input, you get a solution which is either within a multiplicative factor of alpha of the optimum, okay? And I think last time you saw there's sort of an not entirely consistent, it's not entirely consistent within the field whether you talk about alpha being bigger than 1 or smaller than 1, but you can always infer the meaning from the context, right? So if, for example, you have a minimization problem, okay, then you might want to talk about your approximation being at most alpha times the optimum. And this is the language that you're going to use if alpha is bigger than 1. Or you might use it as being at most 1 over alpha times the optimum if alpha is less than 1. And you can tell from context what's being said. Similarly, if you're trying to maximize, then you will talk about the approximation being greater than alpha times the optimum if alpha is less than 1, and being greater than the optimum divided by alpha if alpha is greater than 1. So, right, it's always clear from context which direction we're referring to. And we pointed out that if you want to talk about these sorts of approximation factors, in general, you can't compare to the actual optimum because you can't find the actual optimum to compare to. So instead, you compare to various bounds on the optimum. And a lot of approximation algorithms, a lot of the creativity is in identifying suitable bounds to compare to. Okay? And so we started last time by looking at one standard approach to approximation algorithms, which was greedy algorithms. Okay? And I mean, especially with greedy algorithms, there's often not much to be done in terms of defining the algorithm. The cleverness comes in figuring out what are you going to compare the output of your algorithm to? What are the bounds that you're going to use to compare to the output of your algorithm? All right? And last time, we showed you max cut, right? Where we showed that the greedy algorithm cuts m over 2 edges at least, okay? And if it's cutting at least half of the edges of the graph, then since m is a upper bound on the max cut, that makes this, well, I'll say it my way, a 2 approximation, since the max cut is at most m. And that's where we left off last time, right? So were there any questions about that past stuff before we dive into, before we pick up from there? Okay, so let's just dive in and start looking at another greedy algorithm solution. Let's talk about the set cover problem. Okay. So in the set cover problem, you've got a collection of n items. Okay. And you've got a collection of m candidate subsets of these items. And your goal is to cover all of the items which means you want to pick a collection of subsets whose union is all the items. And your goal is to use the fewest possible, or the smallest possible number of subsets. To cover everything. Okay? So that's the problem. And it is NP complete via standard reductions. Okay, so exact solutions are out of reach. So if you were going to try to develop an approximation algorithm for this problem, then the first thing that you should think about in any approximation algorithm is what kind of greedy solution might work. So what would be a greedy algorithm, or what would be a step of a greedy algorithm for set cover? So, we're thinking the usual greedy algorithm approach. We've made some kind of progress. We've covered some of the items. What would be a next step that would be greedy toward progressing towards the solution? Yeah?
The set which covers the maximum amount of non-count items.
Exactly. So the greedy algorithm just says in each step, add to the cover the set with the most uncovered items. And again, the cleverness here is not in coming up with the algorithm. That's pretty natural. The question is how we analyze it. Okay? So for max cut, we were able to analyze against a single, very obvious bound, the total number of edges. Okay, the question is, what sort of bound do we analyze against when we're doing set cover? Okay, in terms of the number of sets that we end up using, how can we compare that to optimum? So for that analysis, okay, let's suppose that the optimum is some value k. It is possible to cover all of the items with some collection of k of the subsets. Okay. If that's true, what can we say about the progress that we make by choosing the best set? Let's start right at the beginning. We haven't taken any sets yet. We know that k sets suffice to cover everything. How much progress are we going to make on the first set? Yes?
At least n over k.
Right. So k sets suffice to cover all. And that means that if there are, that means that the first set, the first best set, will cover at least n over k items. Right? Just by an averaging argument. If the k sets together cover all the items, then one of the sets has to cover at least n over k of the items. Right? Okay, we can generalize this. Okay, in any step, okay, if our items are still uncovered, then what do we know when we do our greedy selection? This is a little confusing thing. We might have already picked some of the optimum sets, or we might not, because we don't know what the optimum is. Yes? Exactly. If R items are still uncovered, at least one of the optimum sets will cover R over K of the items, which means we will reduce the uncovered set size to R minus R over K, which I can also write as 1 minus 1 over K times R. Okay? And what's important about this is that it is a multiplicative decrease in the number of uncovered items. Yes? So if I run T iterations, they're going to reduce the number of uncovered items n to how much? Yeah? Exactly. It's going to geometrically decrease. Right? All right. Well, that's nice. But is it nice? I mean, it's never going to reach 0, right? We want all of the items to be covered, and that means we need the number of uncovered items to be 0, and we're never going to get there. I mean, according to this formula. But I claim we're actually okay. Right? When can we stop? Yeah? When it's less than 1. Exactly. So we can stop when the uncovered formula, this quantity here, is less than 1, right? If the formula says that we have less than 1/2 of or less than 1 covered item, or if we have less than or equal to 1/2 of an uncovered item, well, the number of uncovered items is an integer. So if it's smaller than 1, it must be 0, right? And we use this a lot, right? That there is an actual difference between 1 and 0. And you can't get lost in between them. So in order to figure out the number of iterations, we just need to solve 1 minus 1 over k to the t times n should be equal to, say, 1/2. Right? And at that point, we're done. Okay. And so we can approximate this formula as e to the minus t over k n should be equal to 1/2, or 1 over e, or whatever quantity you want. And what this tells us is we can stop when t is equal to order of k times log of n. Okay? Once we set t equal to k log n, the k is destroyed by the division by k, right? And then we're left with log n, which cancels the n factor. Okay? So going back up, right, we're able to find a solution after k log n iterations, which means we've used k log n sets. This compares to an optimum of k, and so that means that we have an order log n approximation. Any questions? Yes.
Doesn't the O factor actually affect the factor of the approximation?
Well, the point is that the O comes from my being sloppy about exactly how much I approximated here and so on and so forth. But the point is that it is a fixed constant, right? I think actually if you do this carefully, you find out that it's like natural log of n plus a little bit, okay? And so this is just saying that, I'm not specifying what the base is, but there's some base where you can achieve an approximation of that base. Okay. But notice that, this O is universal. I'm not saying that there's a different constant factor for each problem. That would not be an appropriate use of O. right? I'm saying that there is a constant factor c so that you can always get c log n for any instance of set cover. Okay? Notice it's a little bit interesting that this approximation factor depends on the number of items, but not on the number of candidate sets or on the size of the optimum. Right? It only depends on the number of items. Notice also that this is not a constant, right? This does have a dependence on the input. Right? Our max cut example was 2. It didn't matter what the input was. Here we have a dependency. It actually turns out this is a place where the complexity theorists have done their job, and they've shown that you actually can't do better. It's not possible to beat a log n approximation to set cover unless p is equal to np. And in fact, they've even shown quite a bit about the constant. Like they've shown that you can't beat the natural log of n. You can't do half natural log of n or anything like that. But it's really right, the threshold of approximation is at the natural log of n. But I'm not going to show you how that works because this is not a complexity theory class. So you just have to believe me. All right. Any other questions about that? Let me show you a variant on the set cover problem called vertex cover. This will allow me to make another kind of interesting point about greedy algorithms. So in vertex cover, you're given a graph. And your goal is to pick a minimum set of edges that covers all the vertices. In other words, the union of all the endpoints has to make up all of the vertices in the graph. Okay? Now you might ask, why am I bringing up this problem? Because this is actually just a special case of set cover, right? What are the sets if I want to think about this as a set cover problem? Yeah? Exactly. Formally in graph theory, right, an undirected graph is a collection of sets, right? Each edge is a set of 2 vertices, right? So it really is just a set cover problem. And so we can immediately conclude a log n approximation because it's a special case of set cover. Okay. Oh, I'm sorry, I said it backwards. My bad. We want to pick a minimum set of vertices that cover all the edges. Sorry, I landed at 3 in the morning yesterday, so I'm a little spacey. So a vertex covers the edges that are incident on it. Okay? And basically, we want to make sure that every edge has at least one endpoint chosen. Okay? The way I misstated it originally, that's actually called the edge cover problem. Okay? So here we're trying to cover the edges with vertices, just like above we were trying. Well, I'll leave it at that. But this also is a set cover problem because for every vertex, it covers the set of edges incident on it. So the sets are edge sets associated with each vertex. And so you can solve it using a set cover algorithm and get a log n approximation. But it turns out that here, you can do better. You're relying on the fact that what's special about this set cover problem is that each edge is only covered by 2 vertices. Okay? That's what makes this a special version of the set cover problem. Okay? That there are only a couple of sets that cover every item. Okay? Now, how do we use this? Well, what would be, once I've set up this problem, we're trying to cover all of the edges, so a natural greedy approach would be, and not the same one as set cover, but also a natural one, would be to take some uncovered edge, which means that neither of its endpoints is yet in the cover, right? And you know this edge needs to be covered, so you know that one of the endpoints needs to be in the cover. So you could just choose one of the endpoints and add it to the cover, right? That would be the natural greedy algorithm, okay? But it turns out that that doesn't do very well, okay? So for example, if I have a star, I could say, well, this edge is not covered, so I'll take this one and cover the edge. But now this edge still isn't covered, so I need to take this one. And this edge isn't covered, so I need to take this one, right? So that greedy algorithm could end up taking all but one vertex, right? What is the optimum vertex cover of a star? Yeah? Yeah, the center covers everything. So this is off by a factor of n. So that's a bad algorithm, okay? But what turns out to work better, so the standard greedy algorithm would be to just take one endpoint, and that's bad for the reasons that we just saw. But there's a greedier algorithm where you take any uncovered edge, and then you include both of its endpoints. In the cover that you're building. Okay? Now on the surface, this seems silly. I'm being twice as greedy, right? Why would being twice as greedy be smart if being greedy is not smart? So what is beneficial about being doubly greedy? Yeah?
Chose one of those.
Exactly. Right? If you take both endpoints of the edge, you know that you're taking part of what opt did, right? With the star, you were being greedy, but you were always making a different decision from opt. So taking both endpoints is a way of hedging your bets and saying, well, opt wants one of these, so I will take both. Okay? What that means is that each time you cover an edge, you are actually taking one of the vertices from opt. So how many edges are you going to take before you finish? How many vertices are you going to take before you finish? Right? Each step takes at least one vertex of opt. So how many steps can there be? Yeah?
Two, or like the number of vertices that you're going to take is going to be at most 2 times the number of vertices.
Exactly. Right? If you take a vertex from opt in each step, right, that means that the number of steps is at most opt. And that means that the number of vertices I take is at most 2 opt, because I take 2 vertices in every step. And so that means that for this special case of set cover, I have a 2 approximation. Okay? So this is a sort of a more careful, you're paying more careful attention to your bound on a step-by-step basis instead of just talking about the lower bound on the entire problem. Okay? Let's see, what else can I say about the vertex cover problem? Well, one interesting bit of information about the vertex cover problem is the vertices of the vertex cover, the definition is that every edge has at least one endpoint in the vertex cover. Okay? So what can I say about the complement? Complement of the vertex cover. If I look at the vertices that are not in the vertex cover, what can I say about that set of vertices? Yeah? Exactly. No edge connects two of these vertices. Okay. No two vertices are neighbors. Okay. And this is what is known as an independent set. Okay. So the independent set problem is the problem of, or sorry, an independent set is a set of vertices that contain no edge, right? No two neighbors. And a natural optimization problem is what's known as the maximum independent set problem. Okay? To find as large as possible a set of vertices of which no two are neighbors. Okay? And an interesting feature of approximation algorithms is that approximation factors don't carry over. So we have a 2 approximation for vertex cover. There is, in fact, no good approximation for independent set. It's really, really bad, actually. I mean, not even n to the 1 minus epsilon for a small value of epsilon. Okay, so you can have a graph where there's an independent set of size n over 3, okay, gigantic independent set, and you still cannot find an independent set of size square root of n, or n to the 1/3, or even n to the 1/100th. Okay, none of those are possible. And again, this is something that the complexity theorists have proved, unless p equals np. Okay. The way they proved it is with, again, a sort of an interesting extension of the amplification idea. It turns out that you can sometimes amplify relative approximations. So last time you saw how to amplify additive approximations, to take an additive approximation of a certain quality and turn it into a better additive approximation or an exact algorithm. Turns out that you can amplify independent set. If you have a multiplicative approximation for independent set, you can make a better multiplicative approximation for independent set. And I will probably give you a little bit of that on your homework this week because it's kind of fun. Okay. I'll also just mention, so here we looked at the complement of the vertices in the vertex cover. If you complement the graph, okay, if you complement the graph, then instead of looking for, and complementing the graph means you put an edge where there isn't an edge, and you remove edges where there are edges in the original graph, right? In the complementary graph, all the vertices are supposed to be adjacent. Okay. And a subgraph where all the vertices are adjacent to each other is known as a clique. And so the independent set the max independent set problem is also known as the maximum clique problem in the complement graph. Okay? And these are exactly the same problem. It's just where you say the edges are or are not. And so the approximation factors are identical. Okay? Now, why should it be, or how can it be, that you have a great approximation factor for one problem and no approximation for the complement? It's counterintuitive until you look at the math. So the problem with complements is suppose that you have some objective whose value ranges between 0 and 1. I'm just going to be scaling, right? Your objective can range to no vertices, from no vertices to all the vertices. Okay, is the kind of objective function you're looking for. Okay, so if the optimum of your problem is 1 minus epsilon, then an approximation of this optimum by 1 is a great relative approximation. Okay. If there is a right, we're looking at minimum vertex cover, right? So if the actual minimum vertex cover is almost all the vertices, then actually taking all the vertices gives you a very good approximation, right? What would be a graph where the optimum is almost all the vertices or all the vertices? Yeah, a clique, right? A clique graph, you have to take all but one of the vertices to get yourself a vertex cover. Okay, so if you took all the vertices, you'd be really close to the optimum, right? But then the complement, right, which is going to need the things that you don't have, will have an optimum of epsilon, right? But the complement of your approximation is 0. And so in relative terms, right, having your solution be 0 is infinitely off from the correct value of epsilon, whereas your approximation of 1 is within a 1 minus epsilon factor of the optimum 1 minus epsilon. So that's what's going on here. A graph where you need almost every vertex, you can find a vertex cover by taking all the vertices. But if you go to the complement, right, if you need almost every vertex for a vertex cover, it means that the biggest independent set is very small, right? It's close to 0. So if you throw up your hands and say, well, I'm going to take an independent set with no vertices, well, that's a terrible approximation to the tiny independent set that is present. So this is sort of a feature of relative approximations breaking down when you try and take complements. Okay. All right. So I have some more greedy algorithms to show you, but it's 3:30, so let's take our activity break. I've been noticing too many people sitting down. If that continues, I might have to start playing music or something during the break in order to get people up and dancing. So you wouldn't want that. So stand up and get your blood moving again. You know, you could combine that. You could have people jumping on the other's backs while they're doing push-ups. And all right, let's get started again. So to continue our exploration of greedy algorithms, I'm going to introduce you to a particular problem, which also lets me introduce you to a whole subfield of algorithms called scheduling theory. So the idea behind scheduling theory is that I have a collection of jobs, of n jobs in general. And most fundamentally, these jobs tend to have what are called processing times, which in the simple case, I can just represent by a number pj, how long it takes that job to run. We also have a collection of m machines that can run jobs. Okay. And in the particular problem that we're going to look at first, and I'm going to generalize from this very quickly, but the particular problem that we're going to work on for now is that we want to assign the jobs to the machines to finish all of them as quickly as possible. Okay? That is, we want to minimize the maximum completion time of any job. And this is generally denoted by C sub max. Okay. I should also add that these machines can only run one job at a time. Okay. And I will also add that when we assign jobs to machines, we're only going to allow each job to run on one machine. Although I'll revisit that later. So basically, we want to divide the jobs among the machines so as to complete all of them, in particular the last of them, as quickly as possible. Right? Each machine will run whatever jobs are assigned to it. Okay? And so the total amount of time that a machine takes is just the sum of the processing times of the jobs that got assigned to that machine, and therefore C max is the largest of those sums over all the different machines. So is the problem clear? All right. So, and this is often just known as the problem of load balancing. Right? Because what you really want to do is minimize the maximum load, where the load on machine is just the sum of the processing times. Okay? And in fact, in some cases, processing time may be a, what's the word, sort of an ongoing thing, right? You might say, this job needs, n cycles per minute forever, right? And then instead of talking about the completion time, you're just talking about the total number of cycles that you're asking out of each machine. And you're trying to balance that or keep all of them below their limits. Okay? So what would be a greedy algorithm for minimizing load in this way? What is a thing that we could do one step at a time and then think about greedily performing each step.
You can take a job and assign it to the machine that have the least amount of work.
Exactly. So again, back in the 60s, you got your name attached to very simple algorithms. So this is known as Graham's rule. You assign one machine at a time. And you assign it to the machine with the smallest current load. Okay. So again, coming up with the algorithm isn't the hard part. The hard part is analyzing it, right? Comparing the results of this assignment to the optimum solution. And again, we don't know the optimum solution, so we need to think about what are appropriate bounds on the optimum solution that we can compare to. So any thoughts on that? If I just tell you, here's a collection of job sizes, what are some simple bounds on the optimum that you might suggest? And since we're trying to minimize something, we're interested in lower bounds. Right? We're using the usual strategy, which we started last time, of saying, you know, we've got the opt. Somewhere below the opt, we've got a lower bound. We've got our solution, which is at most alpha times the lower bound. And since optimum is between the lower bound and our solution, this is going to imply that our solution is at most alpha times opt. So what are those lower bounds? Yes?
The average sum time divided by
Great. So one natural lower bound is the average load, namely the sum of the PJs divided by M. Right? This is the Lake Wobegon story. You can't have every single machine with below average load. Some machine has to have a load which is at least the average. And that's a great lower bound, but sometimes it's not a useful lower bound, right? If you have a lower bound which could sometimes be very far away from opt, then it's not a useful lower bound because you're not, right? If the lower bound can sometimes be incredibly far away from opt, then then we're only going to be able to prove a very bad alpha because we're relating to the lower bound, and the lower bound is sometimes much less than opt. And if we can only prove a bad alpha, then we're also going to prove, we're not going to have a good approximation factor against that lower bound. So, but when is this lower bound going to be bad? Yeah?
And there's one job that is like super big.
Yeah. I mean, you can stop right there, right? If there's only one job, right, then this is a terrible lower bound, right? A job of size 1, your lower bound is 1 over m. And so forgetting about the analysis, right? If the lower bound is only 1 over m of the optimum, you're not going to be able to prove better than an m approximation for the algorithm, right? So we need some other bound that won't have that problem. Any thoughts? Yeah, an alternative.
Just max.
Good. So another bound is maximum jaw size, max of PJ. Right? Unfortunately, I claim that this also is a weak lower bound. Right? What would be a case where this would be a terrible lower bound and therefore not good for proving a good approximation? Yeah? Yeah, if I have m jobs of size 1, then this lower bound is 1, but the, sorry, did I say that bad? Did I say that? No, so if I have a ton of jobs of size epsilon, right, then I have a tiny maximum, but since I have so many of the jobs, the actual optimum could be significantly larger, and so my alpha is actually unbounded, right? It doesn't, I have no approximation. This doesn't give me any reasonable bound on opt. So I've got these two lower bounds, but neither of them works. What should I do? Yeah?
Maximum is lower bounds.
Good. So if I have two lower bounds that are not working, but I know that they're both lower bounds, I can simply compare to those lower bounds together. And sort of the strengths of one lower bound can overcome the weaknesses of the other lower bound. And that's exactly what happens here. Okay. So neither lower bound works, but they work together. Okay. And there's a very easy proof of this, and then I can make a slightly more sophisticated proof that gives a slightly better bound. Let's consider the last job added to the ultimately lowest load machine. Okay. This is the job that determines the overall runtime of your schedule, right? Sorry, not lowest, highest. Okay, that's your Cmax, and it's determined by the last job that was added. Now, what can I say about that addition step? So first of all, at the moment of the addition, what can I say about the load on the machine that I added it to? Yeah?
It's actually the lowest.
Right. At the moment of addition, that machine had the minimum load. And what can I say about that minimum load? Yeah? Less than or equal to, so that was less than or equal to the current average. And what is the current average less than or equal to? Well, it's less than or equal to the final average, right? The average only goes up. Right? And what's the final average less than or equal to? Well, that was our lower bound, right? So basically, when we add a job to a machine, the work on it is less than opt. Okay? Now we also know that the amount added in that final step was some processing time. And what do we know about that quantity? Yeah?
Less than or equal to max.
Right. That's less than or equal to the max. And so that is also less than or equal to opt. Right? This is the version, this is our first opt, our first lower bound, and this is our second lower bound. Right? So the step that determined max took a machine that had less than opt on it, and it added less than opt work. Therefore, the final load is at most 2 opt. And therefore, Graham's rule is a 2 approximation. Now, you might be getting tired of 2 approximations. You're going to see a lot more of them. There's something fundamental to the universe that causes lots of 2 approximations to come out. But actually, for Graham's rule, we can prove something a little bit better. Okay? So that's sort of the straightforward argument. Okay. The better argument is to notice that we're being a little sloppy here. We said that when we added the last job, the current load of that machine was less than opt. But that ignores the fact that we're actually adding a job, right? So the load on that machine is less than the average from all of the other jobs, right? Not including the job that we're adding. So the better argument is that, in fact, if we're adding, this processing time pj to the machine with current min load, which I will call L, then the average load at the end is at least L plus the contribution from the job that we add, which is Pj over M. Okay. And that means that we achieve an overall load of L plus Pj, right? Because we add Pj to that load of L. But that can be written as L plus Pj over M, which is the final average load, plus Pj times 1 minus 1 over M, right? I just broke up the Pj into a Pj over M and a Pj times 1 minus 1 over M. But this is the final average, or a bound on the final average, so this is less than the optimum. And we also know that Pj is less than the optimum. And so we put these together, and we find out that Graham's rule is actually achieving 2 minus 1 over M times the optimum, and not just 2. Right? And this is meaningful, right? If you have two machines, right, so on one machine, Graham's rule is optimum, because there's nothing you can do except put the jobs on the machine. But if you have two machines, Graham's rule is a 3/2 approximation, not a 2 approximation. Okay. As the number of machines grows, it gets arbitrarily bad. Okay. So, any questions about Graham's rule? Yes? So that's a really interesting question, right? So what we've said about Graham's rule is that you just add the jobs one at a time. We didn't say anything about the order in which you should add them, right? It doesn't matter which job you put on, right? The analysis that we did just compares the load of the job that you added, right, to various things. And it doesn't matter how that load compares to other job loads. It's only comparing to the overall average and the overall maximum. Okay? But that actually gives you room for improving this algorithm. Okay? So you might ask whether this is the best possible algorithm, or the best one we know. And in fact, we know how to do much better. Okay? If you think about what could go wrong with Graham's algorithm, right? What's going to screw it up? What's going to cause it to end up with a really bad approximation factor near 2? What's a bad case for Graham's algorithm? Yes?
Like we add a very big job near the end.
Exactly. If you think about it, the worst thing you can do for Graham's algorithm is give it an essentially infinite number of tiny jobs. Right? What's it going to do with all of those? Well, it's just putting them on one at a time, and it's always going to put them on the smallest loaded machine, so it's going to completely evenly spread them out. Okay? So what we are going to do is give it m units of work in jobs of size epsilon. So overall, m over epsilon jobs of size epsilon, right? And those are going to be scheduled onto your m different machines. You're going to put exactly m work onto each of those machines. Sorry, my drawing is terrible. And you're going to finish up with 1 unit of work on each machine. Then, in your final step, you give it a job of size 1. Okay? So here we have lots of tiny jobs. And Graham's rule has nicely spaced them out. And then we give it one giant job, and it doesn't have anywhere to put it, and it's now a 2 minus, this is tight. This gives you a 2 minus 1 over m factor away from opt. What should you have done in this case? Yeah.
If you put like the big one on, and then you can move the little ones, you can get like 1 plus a little bit.
Exactly. What you should have done was reserved one machine for the big job, and then put the tiny jobs on all of the other machines. Right? That gives you the optimum, and it's less by a factor of 2 minus 1 over m. Okay? So that represents the mistake that Graham's algorithm did. This is a specific case, but in general, how might we want to avoid that mistake? Yeah?
Choose the highest jobs first.
Right. So if you schedule in order, decreasing order, of PJs, which is known as longest processing time first, or LPT, turns out that that gives you a 4/3 approximation. Okay, just that little change. Okay. There is an important difference, though, and we'll come to that in a few weeks when we study online algorithms. Sometimes you get your input a little at a time, and you can't control the order, right? If you're Amazon, well, you know, every once in a while somebody just wants to run a job. They don't tell you in advance which jobs they're going to want to run. You just have to run it when they tell you, and pick some machine in the cloud to run it. So in that situation, you're kind of stuck with Graham's rule, where you just schedule the jobs as you get them. And you might be stuck with a 2 approximation. If you have all the jobs in hand, then you can sort them first and get this 4/3. Now, I'm not going to prove that to you, because next time I'll show you even better approximations for this job scheduling problem. And I'll also talk to you about generalizing the scheduling problem to a vast whole subfield of optimization in algorithms. So, any final questions? No? Okay, then I'll see you on Wednesday. Oh, sorry, I have one thing. I didn't get good response on my survey requesting feedback on sort of the lectures, the recordings, and so forth. And I am going to put in one more request to please answer that survey, because otherwise I'm going to have to do something laborious to make it a required question on a homework, and I'd really rather not do the work. So please fill out the survey.